To lead us through the pump assembly presentation will be Rob O'Brien. Now, Rob's a regional sales manager, been with Cornell, I don't know, 11 years. And I'm going to toot his horn too. He is probably one of the best pump application men we have at the plant. Rob, I'm going to turn the program over to you and you can start building some pumps. Thank you very much.
Oh, the introduction to Cornell. This crew has come and we're going to tape this presentation for training sessions later on. So if you don't mind here, we're going to relocate the speaker and the cameras here for just 1 second. How's that? How's the volume? Is that okay? Okay, good morning again, and welcome to the plant. Historically, this particular session here, the hands-on session, gets more raves and reviews than anything else. You've done the tough part. That classroom stuff is tough. So now we're going to get to do the fun part and get some hands-on experience and see the things that we've talked about for the last 2 days. As Bob mentioned, we've got the best two mechanics in the industry here. Ted and Lyle, the Pump brothers here. They not only have done work here in our plant, but periodically as requirements demand, they've actually gone out into the field, and both of them have spent a number of days in the field doing work and service field work. So that's an experience that I think helps them be able to relate to you, because they not only work here in this environment with all the proper tools, they've been out there in the real world too, and that's invaluable experience. As Bob mentioned, first off, Ted and I say I. Fact is, you notice I didn't wear my coveralls, so I'm not going to be doing much work. Ted's going to, no thank you. Ted's going to start us off here with assembly of a 4RB, which is a back pull-out design. The 4RB is probably the most bread and butter pump in our line. That's without a doubt our most popular model. I'm going to move this mic up here a little bit so I can see. You folks that are standing over here, there's quite a bit of room. Bob Euchre's here in the front row. Come on. You notice the first thing, we talked yesterday in the dealer meeting about the shower curtain shield. This is the shield you can see now on the bracket. I can't really see it, but I know it's there. Ted, maybe you can point out and show out the shower curtain shield that we talked about. This is the isolating part of that bracket that separates the motor or the driver from the moisture or pump end part of the pump. He's already installed the shaft sleeve onto the motor shaft. You notice the bronze sleeve there. And that's to protect the shaft sleeve against the packing. So as you adjust the packing and tighten the packing, instead of scoring the shaft, it scores a replaceable shaft sleeve so that you can restore those tolerances to like new after several years. Before we go on, I'd like to encourage participation. There's an awful lot of knowledge out here in the audience. You folks have been in the field, you've had the experiences, and this is a training session, not a preaching session. We can learn from you too, and your other dealers can cross-train each other. So I'd encourage comments or suggestions or experiences. Bring that out. Let's share that with the group here so that we can all benefit from your experience. Because as Bob mentioned, we built 5,200 pumps here last year. We do use air impact wrenches rather than a crescent wrench. It's just much more expedient. Ted's got another deflector there. This is a rubber deflector that goes on the outside or the pump side of the shower curtain shield, and that's just one more device that helps shield that leaking from the packing away from the motor bearings. This, we talked about wear rings yesterday and what role they play. Ted's got a backside plate here, or the back of the pump, and he's going to install that bronze wear ring, and it's a press fit or interference fit in, so it needs to be pushed into or hammered into the back plate. He doesn't have just a regular hammer. Hold that up, Ted, and show him what kind of hammer you've got. This wear ring is bronze and it's relatively soft. If you take your steel hammer or your claw hammer out of your toolbox and start hammering on that wear ring, you're going to destroy it. So be very careful when installing the wear rings, if you don't do it with a press, to use a plastic mallet, or even if you don't have a plastic mallet, take a 2x4, a block of wood, and you can literally strike on the block of wood and drive the wear ring in with the block of wood without damaging the wear ring. Stop 1 second. You might want to know, how far do you put that wear ring in? Okay. And I want you to listen to the tone of the hammer. The wear ring actually bottoms out in the bottom of that back plate, and when it bottoms out, you'll hear it bottom out, and you'll hear a different tone of the hammer as he's striking it. So listen up, and you'll know when he hits the bottom. Did you hear it? It gets much deeper to sound. And especially with a 2x4, when you're using a 2x4 to drive it, you can really pick up the sound variance. One thing that we're not doing here that we normally do, if you look in the back here, you'll see a solvent tub. Every part, before it's put into assembly, goes through this solvent. Because some of these castings may have been on the shelf for a number of weeks, and all the machining dust that's accumulated in the air, the cast iron dust, can get on these surfaces. And it might impact the installation of a wear ring, or if you're putting a mechanical seal in, or certainly a bearing frame, you don't want any contaminants in that bearing frame. So every part before assembly runs through this solvent bath and is cleaned. But these guys do such good work, they knew they needed to do that, and they've already done so. Ted's going to show us how to install packing. We use preformed die-cut rings, and you notice that they have an angle or a split. They're not cut exactly square. Maybe we could pass one of those around a little bit. Sure. Kind of dirty. I'd like you to notice that the packing is cut on an angle. What that does is it allows it to overlap and seal better. If it's butt or square cut, sometimes the ends don't come together, and it might provide a track for the water to pass. As they install this packing, I'd like you to watch real careful and notice that he rotates where that split is. They're not all in line. He'll stagger them around so that it breaks up any possible water track or water path. This, before we put that in, Lyle or Ted, hold that up. What is that? Lantern ring, very good. That's to provide a gap or a port in the stuffing box so that you can push lubrication in and lubricate the packing. Or if you have a very high suction lift application, sometimes if you're trying to prime the pump, you can literally aspirate or suck air through the packing. One way to stop that is to turn the grease cup in a couple turns, which pushes grease around that lantern ring and seals the shaft so that way no air can get into the pump, and it allows you to prime it. If we're going too fast, or if you have questions, please feel free to stop us here. The question is, what is the lantern ring made of? Standard material is a Teflon. It's a pliable type Teflon, but depending upon application, they're available in cast iron, bronze, stainless steel. It's really a material that's selected for the particular application. But just clear water would be Teflon. And they are split so that if you want to install them after the pump has been built, it's a split ring. You can actually separate them apart and wrap it around the shaft. That way you don't have to completely remove the pump to put a new lantern ring in. Yes, Sal? The question is, how often should you replace that lantern ring? The lantern ring is not a rotating part. It is fixed, does not normally accumulate or assume any wear, so theoretically it should not need replacement. It does not compress like packing does. So when you change the packing, you should be able to reuse your existing lantern ring. This tool that Ted is using is a spud that is the same diameter as the outside diameter of the shaft sleeve. And what he's done is he's put that in there and tightened the packing up so that when he installs it, it'll slide over the shaft sleeve much easier, and there's less chance of the packing getting caught on an edge and tearing the packing or rolling it over the leading edge of the sleeve. I suppose you could do the same thing in the field by either taking some bar stock and turning it that diameter, or even buy a shaft sleeve. and just put a bar inside the shaft sleeve and use the shaft sleeve as your probe. Another thing that we do a little differently, we use studs. Instead of gland bolts, we use studs. So there's no possibility of them getting cocked or bound when you're tightening your packing gland. Standard material is 304 stainless steel to resist corrosion. Ted, maybe you could hold up the split gland. Like the lantern ring, the packing glands are also split. That allows you to remove them, repack the pump, and service it without having to completely disassemble the pump. You can imagine if that gland was not split, it was a solid piece, the only way you could take it off the shaft would be to completely take the pump end off. So by having it a split gland, that provides easier service in the field. When we ship our pumps, the packing glands are shipped with the gland nuts loose. So when you get a pump, the packing gland is going to be loose, but it has this blue Loctite to keep the nuts from backing off. And the reason that we do that is we want you to, when you first install the pump, to adjust the packing properly. How much should a packing pump drip? Once every 6 seconds? What I hear over here? Now you know why I asked the question. We got 72 people sitting here in the audience, and we probably have 50 different opinions. And I have one too, so I'm going to give you my opinion. A rule of thumb, a packed box should drip about 1 drop per second per inch of shaft. So if you've got a 1-inch shaft or 2-inch shaft, you ought to have pretty much 1 or 2 drops per second. And a lot of you are going to say, boy, that seems like an awful lot. In fact, it is a lot. Let the packing run for 1 day at that drip rate, and then you can tighten it down to where you have just a steady drip, 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 drip. And that'll provide adequate lubrication and keep the packing nice and loose and give you a good year's service life. If you are pumping a product that you can't tolerate that amount of drippage, you might want to consider a mechanical seal. And Bob Boss asked, and a number of you had indicated you had experience with mechanical seals. And Lyle will show us later with installation of a seal. Yesterday in Gary Spencer's presentation, he pointed out some of the differences, and one of those differences was a grade 5 fastener. Does that mean anything to you folks? What is a grade 5 fastener? We got 2 comments and they're both right. A grade 5 is less than a grade 8 and it's hard. A typical fastener, or what you might refer to as a stove bolt, is a grade 3. And they're graded by how hard or how much tensile strength they have. And the higher the number, the harder the bolt. Our experience has been if you have a grade 3 fastener or a stove bolt, which many other companies use, after they go out in the field and they've been in operation, they tend to corrode up. And that's great for the people that are putting the pumps together, but for you folks that have to take them apart, this is not a fun experience. The bolts rust up and you can't take them off and you shear the heads off. And then instead of spending an hour and a half servicing a pump, you spend a day and a half drilling and tapping out the bolts that got sheared off. So Cornell uses a higher quality fastener, which is a grade 5, and is much less apt to shear off. So we're still going to get the corrosion just like the other units, but it's a much tougher bolt, and it'll allow you to take it out without shearing it off, and then you don't have to spend your time drilling and tapping the old bolt out. We're assembled through the back side plate. And the next step will be installing the impeller key and then the impeller. And as Gary Spencer mentioned to you yesterday, look at that finish on that impeller. All the shrouds, the exterior shrouds have been machined. That reduces the internal friction in the pump. We have less turbulence, And that's another reason why we have higher efficiencies. Many companies machine only the wearing surface in this area where the impeller runs in the case or in the wearing. We go the extra step and not only machine the running tolerances, but the entire shroud. Something else that's happened here that we're not going to show you, but that has already happened, these impellers, it's a rotative device, and it needs to be balanced. Ted, if you can hold them up on the back, I'm going to bet my money on you. I'm going to assume you've already balanced that impeller. Okay. Notice the high sheen spot. What they've done is put it on a balance machine, which we have over here in the back, and found that there was a heavy spot on the back side of that impeller. So he's taken a belt sander and sanded that away to make sure that that is mechanically balanced. And that'll help us in our bearing loadings and things. So if you are in the field and you replace the impeller, anytime that we ship a part, it's balanced. But if you reduce the diameter, you have to trim the impeller down for a different operating condition. The impeller should be rebalanced. The question is, do we balance that at operating RPMs? The clear liquids pumps are balanced on a static balance machine, which is a mandrel and rollers. It's a static balance. The non-clog impellers, which have a wider vane, are balanced on a dynamic balance machine, and I'm not sure what RPM. I think they're balanced at about 900 RPM. It's a good question.
We have also dynamically balanced or tested this, did a static balance on these impellers and taken them back there to dynamic balance, and these are really good. There would be no advantage to dynamic balance. These shrouds are so close.
It's more difficult to balance as the vane width gets wider and wider, like you see with a solids handling type pump. And that's why we have to dynamic balance. It's actually dual plane, where we balance the front shroud of the non-clogs and then balance the rear shroud, so that both shrouds are balanced. This is an important part that I'd like you to pay particular attention to. And the reason I ask that is, I've been in the field and I've seen how impellers are put on. Okay. What we're going to do is show you what to do, not what not to do. How many of you have ever hammered impeller on with a plastic mallet? Let me see a show of hands. Come on. We don't want you to do that. We don't want you to use a block of wood, a mallet, a hammer, because as you're striking that impeller to drive it on the shaft, that shock load is being carried right through the pump shaft, right to the bearings. And there's a very good chance that you could Brunel those bearings or get flat spots on it. So you've taken the pump out of service to replace the bearings, you put the brand new bearings in, and as you're reinstalling the impeller, you wipe out your brand new bearings. So all you've done is waste a day and a couple $100. Use a wrench to pull that impeller on. And Ted has a grade 8 bolt that he's going to put in the end of the shaft with washers, and with the impact he's going to tighten that bolt up and pull that impeller on. So there's no loading. Ted, maybe you could hold that up for the camera there. You notice he's got large washers on there that go across the face of the eye of the impeller, and it will literally pull that impeller on as he runs it in. And as it starts to bottom out, then he'll take that back out and add another washer on there so that he can get more reach on the bolt. Did you notice the sound or the tone difference when that impeller bottomed out against the shaft sleeve? When you're using your wrench, an impact, or even a regular crescent wrench, you can tell when it bottoms out. And there's no question about where the impeller placement is. The hub of the impeller butts up against the shaft sleeve and positions the center line of the impeller with the center line of the volute. The lock screw that we're going to install is a heat-treated special steel. It's a high-carbon, heat-treated grade 8 bolt. Do not go to the hardware store and say, I want a 5/8 inch by 1.5 inch bolt. It's not the same. These are very special screws. They're designed for high torque and high shock resistance, Plus, they have a nylock patch on them that acts as a self-locking agent. It's a little yellow or little blue patch that inhibits the threads as it's being driven in. And that acts as a vibration-resistant locking compound. Additionally, we'll put a touch of Loctite. Is that like Loctite 301?
This is 242. It's a thread locker. That's not a solid glue. It's not permanent.
Loctite 242 thread locker, and that assists in holding that impeller lock screw in so that it doesn't back out. Anytime you replace the impeller, replace that lock screw. It's a $2 part, and it'll save you a lot of money for an impeller. If that lock screw backs out or breaks off, the axial thrust can push that impeller off the end and take your impeller out. It's an insurance policy for $2. It's money well spent. In our catalog, in the back section is torque values for these impeller lock screws, and it varies depending upon size, and frankly I can't recite all the torque values per size. Make sure you torque that lock screw. If they're too tight or you over torque it, you might stress it and break it. If it's too loose, we're not getting enough torque on that impeller and actually can cause the screw to stretch, and that could break it also. So the torque value of the impeller lock screw is very important. He's going to hold, you notice he's not putting a 2x4 in the impeller or a screwdriver to hold the vane. He's got a channel lock pliers back on the shaft. How many of you use torque wrenches out there? How many are you going to use torque wrenches out there? Okay. But before you put that on, Ted, it might be tough to show, but in all of our pumps, to aid in servicing, we put an additional drill and tap that acts as a jacking screw. Ted, maybe you could thread more or show them out. What those do is as you take the bolts out of the back plate, instead of taking a hammer and hammering on that volute to break it loose, take the bolts out that you've taken out of the back plate and run them in and use them as jacking screws and just tighten them up, and the bolts passing through will literally push the back plate and the volute apart. It's another little field service trick that helps you reduce your field service expenses. Lyle's already installed the suction wear ring in the eye or in the suction spool of this volute, and it was installed in the same manner that Ted showed you. Just taking a plastic mallet and driving the wear ring into the bottom. The question is, do the wear rings have a chamfer fit? They're actually chamfered on both sides. We do taper them a little bit to help get the leading edge started. That's good machining. That thing snapped up there real snug, didn't it? One thing that we've not mentioned yet, in addition to those grade 5 fasteners, we use Never-Cease compound on the threads. So all of the pumps are put together with Never-Cease, which is a corrosion inhibitor that again gives you ease of maintenance in the field after it's been out there several years. You notice he's going from side to side, just like you tighten the lugs on your tire. You just stagger around the clock, and that'll allow it to pull up uniformly and apply even tension or torque on the faces of the two registers. All right, wait a second, Ted. We're going to have a test. We're going to see if you all were paying attention the last 2 days. What is this tube that Ted is holding up in his hand?
Very good.
That's what the shipping department thinks. All right, really, what is this tube called? External hydraulic balance line. What does it do? This is where you say it balances the axial forces and gives you better bearing life. Very good. Thank you. Depending upon pumpage, if we're pumping a very corrosive liquid, the metallurgy of the pump might change, including the balance lines. If it were necessary, we'd make that out of stainless steel. Right now, it's just standard carbon steel and iron tube fittings.
Question.
Yes, sir.
Is Cornell the only one that uses this?
The balance line? The question is Cornell the only one that uses it? To my knowledge, there's not any other companies that are making that their standard manufacturing. We have seen some other companies that have modified their pumps in the field to take a tube from the back pressure area to the suction spool. We're not aware of other manufacturers that are actually normal course of manufacturing implementing that. The question is, do we normally install the gasket dry? Fact is, I don't build them. I'm going to let Ted talk to you about that.
Yeah, the only thing we'll do is we might put a little bit of grease on that to adhere it, but we don't put never seats or any other kind of silicone or anything like that.
I think a good point is we don't use silicone. It's always great when you're the guy putting the silicone on. It's not so great when you're the guy taking it off. So none of our pumps leave here with silicone on gasketing or machine facing. I'm sorry, I couldn't hear the question.
No.
Talking about the ceiling standpoint?
Yeah. No, we don't. They go together, Brad.
How about that? A beautiful picture. After the backplate is on and the volutes put together, we're going to have them install the grease cup. If you remember back when Ted was packing the pump, he put that white lantern ring in there. This grease cup is the storage reservoir for the packing lubricant. And we call it a grease cup, but we really shouldn't, because we don't really want you to put grease in there. Grease is too heavy, and as you try and push it in there, the grease will go into the packing and it inhibits the flow, and grease is really a no-no. What we should call it is a packing lubricant cup. Garlock, John Crane, companies like that make a graphite-based packing lubricant that has the viscosity or consistency like Crisco, the cooking oil. But it's black and it's full of graphite. It's a very, very good packing lubricant, and that's what we fill it with. As you replace that or replenish it in the field, we'd encourage you to repack it with packing lubricant rather than with grease. I can't see. Did you put the grease cup in?
Yes, sir.
Any questions about assembly of a 4RB? One, yes, sir. The question is, how often or frequently do you need to screw that grease cup in to force packing lubricant into the packing? That's really a function of how tight your packing gland is. If your packing gland has been adjusted properly and allowing that drip, 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 drip that we talked of, chances are you're not going to have to do it, but maybe the first or second time you start the pump. You might, again, need to do it if it's a very high suction lift and if the pump hasn't run for a number of days, where the packing might dry out a little bit and allow air to seep back through there while priming. If it's running every other day or so, I would generally say you don't need to adjust that packing or the grease cup. The question is, if it's operating continuously, do you need to go periodically turn the grease cup? Should not, if the packing gland is adjusted properly, should not require any periodic adjustment of the grease cup. That's merely a means to act as a pre-lubricant when you're starting the pump or a sealing when you're trying to prime the pump. but really is not necessary as a lubricant under normal operation. Yes, sir?
What if you take that grease cup off there and then put a freshwater flush?
The question is, what if you take that grease cup off and connect a freshwater flush? Absolutely fine. We see lots of pumps in the field that are done that. Even not necessarily only freshwater, but even a line from the discharge nozzle of the volute right back to the packing gland or the lantern ring tap. Perfectly fine. You then have a means of flushing into the packing and of giving additional lubrication. So that's perfectly fine. The other thing I'd like to point out here, all of the motors that we use are special order motors. And when I say special order, I don't mean they've got a whole bunch of special things, but they have a few unique features that help you in terms of serviceability and longevity and reliability. I don't know if you can see, but if you look at the air vent passages, Ted, maybe you could point on them on that side. Here's the air vent passages here, and this is what's called an open drip-proof motor. What that means is it allows air to come into the motor, pass across the windings, and then expel itself. So the outside air is what cools that motor. So it's got to be open atmosphere and have these open air vents. How many of you live in the area where it gets a little cool in the winter and these motors run and they get nice and warm? Anybody live here where it gets cold? Those make great houses for mice. It's nice and cold out there and they think, boy, this motor is warm. I want to get in there and get cozy. And while I'm here, I think I'm going to chew on this insulation because it's nice and salty and it tastes good. The mice get in there, they chew on that insulation, and then it's 4th of July in the middle of winter. Cornell has rodent screens installed on every motor, and they have this fine mesh, 1/4-inch mesh, that prevents rodents like mice, rats, snakes, things like that from getting inside the motor and breaking down that insulation. An additional feature that might be difficult for some of you, every motor that we order comes with a grease fitting and an automatic grease relief. How many of you think, so what, big deal? Most motors come with at least one plug and certainly sometimes two. So they either don't get any lubrication, or what many maintenance people do is they'll take the top plug out, put the Zerk fitting in, and just pump that thing full of grease. Well, grease doesn't dissipate and dissolve. It's got to go somewhere. It goes right up into the winding of the motor. So after that operator's been out there and he's pumped a pickup truck full of grease into this motor, and then the thing shorts out, he wonders what happened. With these automatic grease reliefs, there's no way he can over-lubricate that motor bearing. Every time he pumps it in, the grease goes in, tracks through the bearing trap, and then expels to atmosphere. It's another little tiny feature that helps ensure the reliability of not only the pump, but the motor. Let's face it, if we got the best pump in the world, but the motor's burned out, he's still not going to get much water, is he? Yes, sir. The question is, suppose that the pump was subject to piping stress because the pipe wasn't properly supported. What is the weakest point? Is it the flange or the bracket or the motor? Probably the best way for me to answer that, it would really depend on where the moment arm is or where the stress concentration was located. And that would be a function of how long the pipe is, the diameter of the pipe, really a lot of application variables, so I can't directly answer your question. Obviously, we don't want to put piping stress on the pump. We want to relieve that. The pump is not designed to be a brace. It's a pump. Generally, if you have excessive piping loads, generally, you'll see the flanges literally break away from the neck, either on the suction spool or on the discharge nozzle. I personally don't recall ever seeing a bracket break between the volute and the motor. Any of you ever had a bracket break, or where else have you seen the pumps break? I think that's a very valid point. I'm concerned about the extreme condition of a fracture. Chances are your scenario is more likely. He's concerned about the amount of deflection that might occur because of that piping stress. That's very valid. So that's one reason. Another reason why you don't want to put piping stress on it. The pump may not break, but it may be deflecting enough to where the impeller is rubbing on the wear ring. Very good point. That's the kind of experience that I was hoping that we could share with each other. Thank you very much. Any other questions about assembly of a 4RB? Good work, man. Thank you. Now comes the fun part. Putting them together is one step, but now we're going to take them apart. I keep using the word "were," but again, I'm not wearing coveralls. It's a team concept here at Cornell, isn't it?
When you run that there, like you said, that water line off the back seat instead of that grease cup, where would you hook that water line in?
The question is, when you're running that flush line or water line back to the grease cup connection, where do you connect that flush line? If it's an outside flush water or freshwater flush, that can come from your faucet. If it's pump flush, connect it from the discharge top of the nozzle, run your line back to the connection here. So it comes off the discharge flange connection. There's a tap at every location on the volute at 90-degree increments, and then the question is, if they want replacement rodent screens, do we get, or does the operator get them from Marathon Electric or from Cornell? Either place. We have rodent screen material here because some motors we might have to buy from a local stock that didn't have screens, so we screen them ourselves. So either company has rodent screens available. We got a die-hard test going on. Who's the proud owner of a white Datsun, license number HJE 437? You have your lights on, sir.
Question on that motor. Open drip is not practical in our application. We spot it going on. We're using TEFCs on almost all of ours. Now, do you have that same motor available for TEFC with the features that we're talking here? Obviously, wouldn't have the screens and so forth, but are you, when you ship one out of here, spec for TEFC, what do you use?
The question is, this gentleman, in his particular application, does not use any open drip-proof motor. He can't tolerate any free exchange of outside air. It's probably wet or corrosive. And there's another motor enclosure which we use a lot of. It's called totally enclosed fan-cooled. And that is a completely sealed motor, and there is no exchange of air from the outside to the inside. It's a sealed winding. And the question is, on those TEFC motors, do we provide rodent screens and the automatic grease release? The rodent screens wouldn't be required on a TEFC because it's a completely sealed motor. So there is no rodent screens, but there is automatic grease release. Every motor that leaves this plant, whether it's a close couple style, long couple, vertical, horizontal, every motor that leaves this plant that Cornell supplies comes with grease reliefs and Zerk fittings. That's a new policy. And that policy was driven by one of our customers, RC Beach, who's in the audience. We historically only put them on close-coupled horizontal irrigation pumps. They use municipal industrial, and they need Zerk fittings also. So he wrote a letter to us and said, would you consider this? We discussed it, and about 6 weeks ago or 5 weeks ago, we implemented that plan. So we got some feedback from you. How can we make ourselves better? We took that advice, suggestion, and have implemented that. Yes, sir. The question is, again, about the flush line. If you're flushing from the pumpage or from the discharge nozzle and running your line back to the tap, would you pick up particles in the pumpage and push that back into the stuffing box or mechanical seal? Yes, you would. So if you are pumping a liquid that is full of corrosives or abrasives, you likely would not want to use that type of flushing method because you would then be injecting abrasives right into your packing area. So if you have particles in the pumpage or abrasives, then you should probably use an auxiliary outside flush system. Any other comments? Yes, sir.
I noticed when we were putting it together, with the packing in there, it didn't lubricate that packing with anything. Ordinarily, out in the field, we do that. We use some sort of lubricant, preferably the one that we're going to be using. But do you not do that when you're putting that together?
The question is, the gentleman noticed when we were installing the packing, we didn't use any additional packing lubricant, like Never Seas or some type of compound like that. Do we normally do that? The packing that we're using is a very heavily impregnated graphite. In fact, when he passed it around, he had to pass it around in a rag because it is very, very greasy. And it's literally impregnated with lubricant. Sometimes I've seen them, and I don't notice today, sometimes they'll actually take the paintbrush and paint the shaft sleeve with Never Seas. I didn't notice, Ted. Did you do that today? Okay. The packing has quite a bit of packing lubricant in it, the particular type of packing that we use. And there certainly is lots of different packing materials. And if you get one that doesn't have much packing lubricant in it, you probably should use an additional pre-lube. Packings that we're using, we don't think it's necessary. Anyone else? I appreciate this participation. It's good, and we can all learn from that type of cross-training experience. All right, Lyle, you're up, big boy. The first thing that Lyle's done here on our pumps that use the external balance line, before he can remove the volute, he's got to take the balance line off because it connects the backside plate to the volute, and the only way you can separate those two is the first by removing the balance line. So that's the first step after you've removed the pump from the field. See, the Never Seas on those bolts. I told you they wouldn't corrode. That's that bronze. Does not corrode. It's beautiful, isn't it? This is my favorite part. I spent a number of years in assembly and field service myself before I got doing what I'm doing now. And it's pretty great to be idealistic and have the right tools and all the right things. But I've been out in the field where I've had to use some pretty bizarre improvisations and maybe even a cuss word or two. They're going to show us today what is the right or proper method to remove an impeller. How many of you have ever taken an impeller off a pump? Okay. How many of you have ever had used screwdrivers? Wedges? I got one. I got a wild one. I had to use an axe one time. Yeah, torches? Lyle is going to show you here we have pry bars. And I'm not sure, you can use the bar puller or pry bars?
We're just going to show these, that you can use them if you pry behind the vanes.
Show them what you mean, prying behind the vanes. If you're using screwdrivers or wedges, make sure that the placement of your pry bar goes right on the vane part. Don't go in between the vanes because as you push out, it could collapse the rear shroud of the impeller. Well, maybe you could even show our TV viewers here. Be sure the placement of that pry bar is immediately behind the solid portion of the vane. We use bar pullers here. The nut that Lyle's got in his hand is a centering nut. The way that we're going to pull that impeller off is by using a bar puller and driving the bolt in, and that's going to pull the whole backplate and impeller off. But so that he doesn't foul the threads in the end of the shaft, he's got a bolt that he's drilled a little dimple in, and he'll put that bolt in the end of the shaft, so then the center of the punch or the bar puller will push against that bolt rather than the end of the threads. You have a question there? You're just glad to be here, right? Some of you didn't get a chance to meet Tom. Tom Godfrey's the man up there with the Cornell badge on. Tom works in our inside sales group. He does a lot of backup and service, so a lot of the times he's the man that's turning the wheels here at the plant. This bar puller is actually all thread. It's nutted on both sides. You put the bolt through till it hits the nut and then nut the back side, and that's going to act as the puller on the back side plate. These, all the impellers, with the exception of our food handling pumps, are a straight bored keyed shaft with an interference fit. So you'll need to use a puller to take them off. Comes off that easy in the field for you fellas, doesn't it? This gentleman's mentioned a rosebud. How many of you know or have ever used a rosebud? Know what a rosebud is?
That was a joke. I don't really do that.
Sometimes it actually has, you got to heat the thing up. A rosebud is an attachment that goes onto a torch that goes around, and you literally heat the impeller and you try and expand it from thermal expansion. We've all probably done it. If they've been on there so long and they're so corroded you can't get them off any other way, a rosebud is a way to try and break them loose from the shaft. That's a good point. As you use a rosebud, there's a possibility that you might get some warpage. So if you've had to use a torch, you want to put it back in a lathe and make sure that it's true and concentric. What these guys are going to show us now is how to remove a wear-ring, I think. Is that where we're at?
Yep.
Frequently we get asked, how do you replace these wear-rings? In many of our pumps we have what's called a blind wear-ring. And when I say a blind wear-ring, I mean there's no lip for you to get a chisel on. The contour of our suction spool or the contour of the back plate matches the same diameter as the wear-ring, and there's really no surface for you to get a chisel on to tap the wear-ring out. So what we do is we'll drill that wear-ring out. And I don't mean you get a drill that's 4-inch diameter and auger the thing out. You take a drill, a very small drill, and start drilling on the wear-ring. Maybe you could hold that up. Have you already got your centering holes?
Yeah. We've pre-drilled it with a small hole right in the middle of the wear-ring.
If you can picture, for those of you that can't see the wear-ring, picture a clock. You drill at 12 o'clock, and then about 1 o'clock, and then the centering holes will allow you to get another drill bit. Then you'll drill in those same locations, and that piece between those two drills will allow you to lift that piece of the wear-ring out, and then the whole wear-ring will lift out in your hand. They'll show you here what I mean, and it'll make more sense. Lyle, maybe you could show him that first drill. He's got a drill bit that's about the same diameter as the width of the wear ring. So you see he's literally drilled a tap or a hole right through that wear ring now. Folks here to your left need to see also. He'll move over a couple inches around the clock or around the diameter of the wear ring and duplicate that, and then he'll be able to lift that piece out. I hear the drum roll. He's going to take a small chisel and a ball peen hammer and tap that wear ring piece out. There's the piece that's been between where the two drill locations were. Now he can lift out the whole wear ring. Didn't have to take a torch, didn't have to take a big machining tool. It's a 2-minute job. Yes, sir.
With this bronze, it's pretty easy to drill those out. We have some of the 10-inch pumps with stainless steel wear ring, cast iron wear ring. Not nearly as easy to drill. Do you have any other methods?
The question is, this gentleman has some very large pumps, 10-inch pumps, that use stainless steel wear rings or cast iron wear rings, which is not as soft as the bronze. And do we have some other methods? I've heard of a lot of methods. I would recommend the same procedure. It just takes more time to drill a harder material. I've also had a number of people in the audience tell me in the past, if they take a welding rod and weld around the ID of the wear ring, it causes the wear ring to shrink up, and then it'll fall out that way. I've also heard about them using dry ice. If you pack the volute, put a piece of cardboard on the bottom, and pack dry ice in there, it gets so cold the wear ring contracts, and the wear ring will lift out that way too. There's a lot of different tricks, whatever seems to work best. The drilling method for us, it wouldn't be practical for us to have dry ice around here. The next step in our training session here is going to be sleeve removal. This is the one that always attracts lots of interest. What Lyle's going to show you is the two typical methods of sleeve removal. Now, I've been in the field a number of years, and I've seen sleeves come off with chisels, torches, hacksaws, cuss words, taking the rotor out of the motor and putting it in a lathe and turning it. I mean, I've seen a lot of different ways. We're going to show you an impeller or a sleeve removal, and also a practical means for you to do in the field. And watch this. This is a pretty neat trick that'll help you and save you a lot of time and anxiety. This is called expansion by peening. What he's going to do is he's going to hold a hammer on the bottom side of the sleeve, directly opposite the hammer that he's holding tight against the sleeve. He's going to strike with another hammer on the top. And he'll slowly repeat that process, moving it towards him. Then he'll rotate the shaft about 1/8 of a turn and repeat it. What's happening is the energy that's being imparted into that sleeve wants to pass through the sleeve, it hits the other hammer and deflects back up. So all that energy is being absorbed by that shaft sleeve, and it'll actually cause it to swell, and he'll be able to just slide it off in his hand. Saw a question up here. The question is, what happens to the bearings? Very good question. If the hammer on the bottom is not held snug, you're going to beat your bearings to death. If the hammer is held tight on the bottom of the sleeve, the energy that's going through is being absorbed by the hammer and is not being transmitted to the bearings. Again, if that hammer on the bottom is loose, you got big problems. Do not do that. You're not only going to have bearing trouble, but you're going to bend your shaft as well. So it's critical that you hold that hammer on the bottom very tight, and you'll notice the size of the hammer that Lyle's got there. He's got a pretty large mallet there, so it's got a broad surface area, and it can absorb a lot of energy.
The hammer on the bottom, does it have to be a hard surface like that, or something like 2x4s stacked up underneath? Does that work?
The question is, does the bottom device have to be a hard surface like a hammer, or could we use 2x4s? Absolutely has to be a hammer. If it's soft like wood, you know, a lot of us think wood is hard. It's pretty soft, and that energy will just soak into that. So you'll just push it right through the shaft, bend the shaft, and take the bearings out. So the bottom device has got to be just hard as the hubs of hell. Well, what you might do is now come around to this side so these people that you had your back to could see what you've done. Look at that. Think about in the field how many times you guys have been out there and cut and hacksawed and torched. It's pretty simple, isn't it? The comment about the bronze wear ring is also true about the shaft sleeves. This sleeve is bronze. If you have a stainless steel shaft sleeve, you can do it with stainless, but it's going to take more time. It might be a 5-minute process instead of a 2-minute process. Lyle, we have a doubter in the audience. Yeah, they said they want you to pull on that sleeve. They don't think it was really on there tight.
It was.
Yeah. The next tool or device that Lyle's going to show us is a sleeve puller. And this basically is a piece of steel or collar that we've made here and drilled and tapped with the set screws or locking screws. He'll slide that over the diameter of the sleeve, lock those screws down, and then he'll put a bar puller on or a gear puller on that whole sleeve puller and pull it off that way. Likely many of you don't have that in your toolbox in your service field truck. So the peening method is something that you can do in the field.
Yeah, it's scrapped when we're done here.
No, I mean the puller. Huh? Said you ought to market that.
We're trying to sell pumps, not gear pullers.
Again, we're protecting the threads in the end of the shaft.
Lyle again has noted that he's protecting the end of the threads in the shaft with the nut there at the bottom. He's locked the sleeve puller onto the sleeve, and now he's going to pull the whole assembly off. From a time standpoint, it's just about the same amount of time, whether you use the puller or the peening method. Good work, man. Very nice. He says, I'm out of here. Our next session is going to be on the assembly of the new F-16 modular frame and assembly of a mechanical shaft seal. In the essence of time, they've already mounted the bearings on the shaft, put the shaft sleeve on. That raises a question. How do you install shaft sleeves? We've had interference fit. This gentleman's got an idea. Gentleman says the way they install them is they take the shaft sleeve and put them on a heater and expand it, thermal expand the sleeve, and then it'll just slide on the shaft. That's how we do it at Cornell also. We have an oven here somewhere, and when lunch isn't in there, they put shaft sleeves. bearings, we have both a press to press bearings on, and we also have a bearing heater. And I'm not sure which method they use here or which they use more. Are y'all familiar with bearing heaters? Heats the inner race of the bearing and expands it the same way the shaft sleeve, and then it slides on the shaft, and you don't have to hammer the bearing or load it or do any mechanical damage to it during installation. Again, this bearing frame has already been all washed out in the solvent tub, so we're sure that there's no particles or contaminants in that bearing housing. And they're designed so that you can load the entire rotating assembly into the bearing cavity as a complete rotating element, I think. We use a bearing fits called a C3 clearance bearings, and in the housing is called a J5. In other words, it's a slip fit in the bearing, so we allow the outside of the bearing to slip into the bearing housing. Notice again that with this new bearing frame, the external or the shower curtain shield also incorporates a lip seal that acts as the front bearing cover in this new bearing frame design. So the shower curtain shield is really providing dual service there as a bearing cover and then also as a shield from the pumpage. In our present design, the oil loop frames use double lip seals. In this new Harvey frame or the modular frame on the F-16 and F-18s, both oil and grease lube use lip seals. The oil frame is going to use 2 lip seals as our present design, and the grease lube frame uses 1 lip seal. The question is, did the front bearing have an external snap ring? I didn't notice it. Ted?
No.
It's held in place by the bearing cover or the shower curtain shield. There is no snap ring on this particular frame assembly. What Ted's doing now is measuring or miking the tolerance for axial end play. Since we have some casting variance and machining tolerances, our machining tolerance here at Cornell are plus or minus 2 thousandths. So every part is machined to within 2 thousandths of an inch. If by chance all of the stack up or shift was in one direction, say the bearing frame was shifted too far one way and the bearing cover was shifted too far the other way, it's conceivable that we might have 6 or 7 thousandths clearance. What they want to do is measure that axial end play and put in bearing spacers or shims to make sure that the axial tolerance is correct. And I believe on this frame it's 7 to 10. Sorry, 3 to 10 thousandths. Axial end play is the amount that the shaft moves forward or backward, 3 to 10 thousandths. Yes, sir. The question is, if we know this is a hot oil pump application, do we allow for increased clearance? The clearance that's accommodated because of elevated temperatures in a hot oil pump is taken up in the bearing, the C3 fit of the bearing, and we do not add additional clearance for axial movement, whether it be hot oil or a refrigerant pump. There's one comment here, and I'm not sure that it came up during the conversation over the last 2 days. We talked about the bearings, the double volute design, the balance line. I'm not sure that anyone talked about shaft material. Did that come up in anyone's conversation? Anybody remember about shafting material? Cornell uses a shafting material called stress-proof steel, which is an SAE 1144. Basically, it has mechanical properties that are considerably higher in terms of tensile strength and bending resistance strength as compared to, say, a 1040 or 1041 or 1045, which is common shafting material. So apparently no one talked about it, but even the raw shafting material is a vastly superior product, has less tendency to bend, and that's another reason why we can run our wearing clearances much tighter. What Ted and Lyle are doing now is showing a mechanical seal installation. I'm going to move over here so I can watch. In Ted's hand is the seal gland, or it takes the place of a packing gland with a mechanical seal. The stationary seat is already pushed into the seal gland. Not yet, I lied to you. He's going to do that now. The question is, what type of seal do we use? The manufacturer, the primary manufacturer that we use is John Crane, and they have a number of seal types. For a typical water application, we use a type 1, which is a rubber bellows type seal. For hot oil, we use a type 715. We use a number of different types of seals dependent upon the application. This particular seal is a John Crane type 1 with ceramic stationary seat, which Ted is holding in his hand there. That portion of the seal does not rotate. It stays fixed in the seal box or in the seal gland there. Hold that white card up also, Ted. The seals that you get from us or from the factory come with packing on them and cardboard face covers. Use those to put on the seal face to push them in with your thumbs. Even a little bit of oil that's on your finger, if you push on that seal face, it could keep that seal from sealing. So make sure you be very, very clean and use those covers. These seals are flat to within about 23 millionths of an inch. 23 millionths, not thousandths. They're literally, they're so flat they're within light bands. There's a machine that measures light bands across. That's very, very flat. So if you got your hands that you think are clean and you got lots of oil and things on them, it could impede those faces from coming together flat. Ted's pushing the additional rubber deflector ring on that prevents oil or leakage or water coming back towards the bearing frame. One thing I'd like to point out here, Ted's been doing this a number of years, so he's already got all the tricks of the trade. Notice that he already installed these with the gland bolts in the gland. Because as he puts the back plate up here, it's going to push the gland plate so far back, he's not going to have enough room to get the bolts back there. So he's already put the gland bolts in so that he doesn't have to try and reach in there afterwards. Lyle made a point here that the bearings were not lubricated, but under normal operation or assembly, certainly they would be. What is that you put on the sleeve there, Ted? Is that, looks like honey. He's put STP on the shaft sleeve, and that's to allow the bellows to slide onto the sleeve, but be very careful not to get this STP on the seal face. It's only intended to be a lubricant on the bellows. Let's show them what a bellows is. See the black part inside that seal cage? That's the rubber portion or neoprene portion of the seal that seals to the ID of the seal and the OD of the shaft sleeve. And that'll actually go onto the shaft sleeve and seize onto it. But right now we want it to slide, and that's why he's put the lubricant or the STP on it. Sliding the rotating assembly back to where it almost contacts the stationary seat. Now we'll put the spring portion on. Notice here before, you know too much, Ted.
Sorry.
Our TV viewers here need to see what you're doing. Notice at the bottom of the spring is a seal pusher. This brass washer that he's holding in his hand, that goes against the hub of the impeller. And that's what will act as a contact surface to compress the spring. The next, and this isn't in every pump, it depends on the particular model, Some use a seal spacer, which is shown here, which is made of stainless steel. And that will press up against this bronze plate on the seal side and against the impeller hub on the impeller side and provide proper compression on the spring and load the seal face. You notice he didn't install the seal into the back plate and then try and put the back plate onto the shaft, because you're going to have a big plate and you're trying to do this. Chances are you would damage the seal. So he's installed the seal onto the sleeve and then he's putting the seal housing or seal box on.
Go ahead, put the impeller on after that.
The next step that they would do would be, before they pull the seal gland up, the impeller would be put on to provide a backing or the driving force of the spring, and we've already shown you how to install the impeller. Once the impeller was on, impeller locks were put in and torqued, then he would pull the seal gland up to bring the seal into compression. And when you're tightening the seal gland, it's done the same way. You tighten one bolt, go to the diagonal corner, tighten the next one, and stagger around so that you get uniform compression of that spring. Rather than trying to tighten down 2 bolts on one side, it might cock it. It's just like you tighten the lug bolts on the tire of your car. You want to stagger around so you get uniform loading. Any questions about assembly of a mechanical seal or anything we've gone over this morning?
I have a question for you.
Yes, sir.
You use STP, did you find it superior to motor oil or other?
The question is, we use STP. Do we find that advantageous or superior to even, say, motor oil? I generally say that STP is much slicker and doesn't wipe as cleanly as oil. Oil, if you push that bellows over it, it'll literally just push the oil away, where STP hangs in there longer and gives you better lubrication surface. I'm not advocating that you load the bearing frame with STP, only for lubrication of assembly things. Be sure and check the bearing frame guide for the proper type and amount of lubricants. Yes, sir. The question is going back to the ceramic stationary of the seal, the white part. Is one side smoother than the other? Yes. I believe, and we have the John Crane man here, the seal face that's been lapped or faced is smooth and polished. The seal face that normally has a felt mark on the back. Am I correct there, Dave? So, can you use the back side without having it lapped? So the face that does not have the felt marker on it is the face that you want to be towards you, or towards the rotating portion of the seal. Good questions. Any other questions? We either transferred the information good or we bored you. I'm not sure which. Yes, sir.
On your motors, do they make a stainless steel cast iron junction box or application areas?
The question is, on the motors, are cast iron or stainless steel junction boxes available for high moisture application? I'm not sure about stainless steel, but absolutely with cast iron. The Marathon motor, which is a blue chip series, totally enclosed fan cool, comes standard with cast iron junction box. The open drip proof, I believe, is a steel box, depending upon the motor frame size. If you get into the larger frame sizes, Jim, I think you're here, he was here with us, the Marathon man. I think after about 326 frame, they go to cast iron J boxes. On all of the TEFC, though, they are cast iron. And I suspect we could get stainless steel, but that'd probably be a special order. Yes, sir.
Change from packing to change this type of seal. You change black plate.
That's a great question. The question is, if you have a packed pump and you want to change it to a mechanical seal, do you have to change the back plate? Sometimes you do. It depends on the pump design. In the bottom of this back plate is a little bit of a lip that the packing seats against or the packing washer. And in a mechanical seal, you wouldn't want that. It's likely you could use the same back plate, but it might require a machining process to machine that lip out. Some seal boxes are designed to have the seal actually bottom out. So I can't answer you categorically. It really is model specific. If you have some that you want to do that with, if you give us the serial number, we can check the bill of material and check the parts and advise you what would need to be done to make it convert from one to the other. Yes, all backplates are drilled with 4 bolt holes, whether they be packing or mechanical seal. Yes, sir.
Yeah, when you're converting over from packing to this mechanical seal, what is the rough cost of conversion as far as the seal itself? Replacement cost?
Is this a trick question? The question is, when you're making your conversion from packing to mechanical seal, what is the conversion cost? Again, that varies depending upon the model, whether you need a new backplate, whether you don't. Seal size, are we talking about a 1 5/8 inch seal or a 3 inch? Very difficult question to answer, and it really would have to be more of a model number specific. It could be as low as maybe $300 or as high as maybe $5,000, depending upon the seal and the pump size. Any other questions? I want to thank you for your questions and your attention. Our next step in the session this morning is castings, and to make that presentation is Al Alt, Wally Westlink, and George Bardsley. But before I turn this over to Bob Boss, I'd like to thank both Ted and Lyle and acknowledge the job they did. Good job, man. Bob and Mr. Boss.
Thank you very much, Rob. Good presentation. Maybe you'd like to stand up and stretch.